And a very good morning to everyone. Distinguished guests, respected judges, esteemed participants, and dear audience member, welcome. We kindly invite all guests to get ready as the competition will be common shortly. Please ensure that your devices are switched to mute to avoid any distraction throughout the program. Thank you for your cooperation. Once again, good morning. I am Muhammad Fikri Beroslan, and it is my honor to serve as your master of ceremony for today's event. Ladies and gentlemen, we are gathered virtually for the UTHM Material Lecture Competition, MLC 2025, and your presence, attention, and enthusiasm are truly appreciated. To commence our program, on a blessed note, we will begin with a dua to seek Allah's blessing and guidance. It is my pleasure to invite Mr. Zulhafizi bin Jaidi to lead the prayer. Tafaddal mashkura. Al-Fatiha.
أعوذ بالله السميع العليم من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وصحبه أجمعين. Ya Karim, Ya Wadud, indeed we are gathered here to express our appreciation for your amazing gift. Make us your servants who are always thankful, whether it is small favor or large favor. Ya Rahman, Ya Rahim, we hope your blessing for the material lecture competition, MLC 2025, concluding program. We must be aware that we wish to benefit from your rahmah, inspire us to adore everything this is good, and make us, our lecturer and our leaders, continue istiqamah, high devotion, and strengthen the community, society, nation, and country. Rabbana atina fid dunya hasanah wa fil akhirati hasanatan wa qina adzabannar. Allahumma salli ala Muhammad, Allahumma salli ala Muhammad, Allahumma salli ala Muhammad. Alhamdulillahi rabbil alamin.
Amin, Amin, Ya Rabbal Alameen. Thank you, Mr. Zulhafizi, for the dua. On behalf of the organizing committee, I would like to extend our warmest welcome to all participants and guests joining us today. For your information, UTHM MLC 2025 is proudly organized by the UTHM IMM Student Chapter under the guidance and advice of Associate Professor IR Dr. Sufiza Ahmad. To share more about IMM Student Chapter and the material lecture competition, I am honored to invite Associate Professor IR Dr. Sufiza Ahmad, advisor of UTHM IMM Student Chapter, to deliver the opening speech. Please welcome.
Assalamualaikum and very good morning. I extend a warm welcome to all those gathered here today, physically and virtually, including our honorables, judges, and distinguished participants. Welcome to UTHM IMM Materials Lecture Competition. First of all, I'd like to express our gratitude to our honorable judges, IR Dr. Azura binti Ismail, Dr. Nur Azam Badruzzaman, TS Dr. Muhammad Azham bin Azmi, and Professor Dr. Hassan Zuhudi bin Abdullah as our head judges for today's competition. Thank you for your providing your valuable time and support today. I would like to share a brief introduction on the background of materials lecture competition in short term, we call it as MLC. The MLC is the brainchild of the Institutes of Material Measure, IMM, to give a platform to young students and researchers for public and private University as well as form the industrial in Malaysia to showcase their ability and to communicate the research on the works for projects related to materials to a diversified audience. The first national level MLC organized in 2012 by IMM. Of course, this competition does not stop in the national levels. After the national level MLC, the competition continued to the Young Person World Lecture Competition, YPWLC, where the winners of the finals held in country and region where the Institutes of Materials, Minerals and Minings, IOM3, has international branches compete in the world finals. Since 2020, the Young Person World Lecture Competition is being held online. For your information, our university, UTHM, started taking part in national levels, MLC, in 2018. Therefore, this will be our 8 years participants, inshallah, where the winners of UTHM, IMM, LSC 2015 will be our representative at the national level MLC that will be held in October 2025. Before concluding my remarks, I would like to express my appreciation to the UTHM IMM Materials Student Chapter Committee for their hard work in organizing this competition. Your commitment toward this program today and for the 7 years last, I very appreciate. To all participants, all the best and good luck. I rest my speech today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Associate Professor IR Dr. Sufiza Ahmad, for such an inspiring address. Now, ladies and gentlemen, it is my pleasure to introduce our esteemed panel of judges for today's competition. Our first judge, the incredible Professor Dr. Hassan Zuhudi Abdullah. Our second panel is the amazing Dr. Nur Azam Badaruzzaman. Our third panel of today, the famous TS Dr. Muhammad Azham Azmi. And last but not least, the one and only IR Dr. Azura Ismail. We are truly honored to have these distinguished experts with us today. Please be reminded that all decisions made by our judging panels are final, and individual scores will remain confidential and we will not disclose or discussed. Here are the rules and evaluation criteria. Participants will be evaluated based on following criteria. First, structure of the presentation and clarify of explanation and argument. 2, standard and professionalism of presentation. 3, personal enthusiasm for the subject matter. 4, ability to deliver the presentation in the compelling and engaging manner. 5, technical depth and accuracy of content. 6, clarity and relevance of any visual aid used. 7, ability to provide a concise and meaningful summary at the end. 8, adherence to the allocated time limit. And last, ability to respond effectively to judges' questions. We also request our audience to refrain from providing any guidance, prompts, or hints to the participants during their presentation, as they may disrupt the competition process. Thank you for your kind cooperation. Okay, let us now to proceed with the competition. We go to the first contestant today. Please welcome Miss Natasha Sasbila with her presentation entitled Aluminum Nitrate Thin Film Deposition Using Industrial Grade Sputtering System. Please welcome.
Have you ever wondered what makes your 5G phone, electric car, or satellite communication work faster and more efficiently? The answer lies in advanced semiconductor materials. One of them is aluminum nitride or ALN. Let me introduce you to the superstar of this talk. So, what is ALN? ALN is a chemical compound made from aluminum and nitrogen, and it belongs to the group 3,5 compounds, just like gallium nitride and indium nitride. You can see several real-world applications of this semiconductor material, such as in the high-frequency domain, in the high-power system, and most importantly, ILN can be found in which combines both high-frequency and high-power capabilities in one device. For that purpose, mostly ILN is produced on silicon wafers. Sounds very wonderful, right? Now, let's talk about the current concern regarding ILN on silicon wafers. If we look at the current market, most companies such as Kema Technologies, Increase Semiconductor, Mitsubishi Chemical, Dowa, and others, they are still focusing on 2 until 6-inch wafer. So there is a clear demand and opportunity to shift towards 8-inch wafer production, which supports a next generation device through lower costs, higher yields, and of course, contributes to the industrial scale production. Because when we increase the wafer diameter, we can fabricate 25 to 40% more chips per wafer. But it's not as easy as it sounds. Scaling up the wafer size introduces a major hidden challenge. Achieving film uniformity across the large surface area so that the entire wafer can be utilized efficiently without material waste. So, here we are. Hi, I'm Natasha, and today's lecture will discuss the ALNs and how it can be applied in the 8-inch wafer by using industrial-grade sputtering machine. So, what makes ALN sounds very interesting? ALN has excellent properties, such as high thermal conductivity of around 320 watts per meter Kelvin, a wide bandgap of 6.2 electron volts, strong piezoelectric response, and excellent chemical and thermal stability. Several methods can be used to synthesize or fabricate ALN, such as metal oxide chemical vapor deposition or MOCVD. Then we have atomic layer deposition or ALD. The next one is molecular beam epitaxy or MBE, and the last one is pulse laser deposition or PLD. However, these methods are typically expensive, complex, and more suitable for small wafer sizes only. This is where magnetron sputtering comes from. This method offers a solution by providing better control and higher deposition rates. However, most of sputtering systems use only 3-inch targets, and the use of larger 12-inch system is still very limited. So, in this lecture, I try to explore the ALN film growth using the 12-inch system or industrial-grade machine that support for large wafer sizes fabrication. Then, how can we make sure that our ALN film has a high uniformity? The answer is in the rotation speed setting that we use. This parameter sounds underrated, but believe me, this parameter is very strong in influencing the uniformity across the 8-inch wafer. This parameter can ensure that all of the wafer surface is equally exposed by the target and make the film have homogeneous nucleation and crystal growth. Then, I will introduce you to the big machine here. So, this is the industrial grade sputtering machine equipped with a 12-inch aluminum target as the aluminum source, and we use nitrogen gas as the nitrogen source. So, the final product will become ALN. As I mentioned earlier, we will focus on the rotation speed parameter, and we have several variations related to this parameter as shown in the slide. Are you curious what will happen when we give power to the aluminum target and at the same time we also flow the nitrogen gas to the chamber? Of course, the ALN material will be produced. You see this pink-purple light? This is called plasma ignition. And this is the indicator that aluminum target and nitrogen gas interact with each other. For your additional information, this chamber is in the vacuum condition with a pressure of 1 multiplied 10 minus 7 torr. You can imagine that even a fly and ant can die in this environment because our normal atmospheric pressure is 756 torr, not even minus. During the deposition process, we maintain the stability through optical emission spectroscopy measurement with the setup shown in the slide. From the optical emission spectroscopy, we can clearly see that there is several spectrum representing the aluminum and nitrogen atom. For the argon atom, don't worry, they will not react with aluminum and nitrogen since they are inert and just function in releasing the aluminum atom from the target. Then, this is the deposit ALN film. To better analyze the effect of rotation, we group the settings into 3 regions. Region 1, where target rotates faster than the substrate. Region 2, where target and substrate rotate at the same speed. And the last one is region 3, where target rotates slower than the substrate. From this figure, we can see that the film from 10 per 10 RPM setting shows a more uniform color, indicating better thickness uniformity. From figure A, we obtain that in region 2, the standard deviation value is lower compared to region 1 and 3. This shows that in region 2, the film thickness remains relatively consistent with only minor fluctuations. Figure B shows the deposition rate, which also follows the same trend. The last one is figure C, shows the coefficient of variation or COV value. Lower COV value means a higher uniformity, and again, the 10 per 10 RPM condition offers the best uniformity. Here is the AFM result. As the rotation speed increases, we observe the increase in the grain size and a decrease in surface roughness. This suggests smoother surfaces can be achieved with a higher rotation speeds. Moving to the XRD result, figure A shows the strongest 002 peak at 5 per 5 RPM, indicating a strong Z-axis orientation. However, the 10 per 10 RPM setting, while not having the strongest peak, shows the lowest FWHM, strength, and dislocation density. Lower FWHM, strength, and dislocation density indicates a better crystal quality and lower lattice distortion. Therefore, we conclude that 10 per 10 RPM offers the best overall crystalline quality. Now, we have the morphological properties of the ALN. ALN with 002 orientation has a columnar structure, as we can see from the cross-section image. Also, to confirm that our film really consists of ALN material, we have the EDX results here. And it is clearly obtained that our film consists of aluminum and nitrogen atoms, with silicon as a wafer. If we see from the top view, we will obtain that actually the morphology of ALN002 is a hexagon-like structure with a view dislocation that occur and related to the previous XRD results. Okay, we already know about the properties of ALN with varying rotation speeds, and we know that the best rotation settings are achieved using 10 RPM for both target and substrate rotation speed. Then what's next? Of course, we need to study the uniformity across the entire wafer, right? First, we will see from the 2-inch wafer, from the film thickness, surface roughness, crystalline quality, and also electrical properties, it shows a consistent result across a 2-inch area. Okay, we tried to make a larger area, which is 4-inch wafer. This result also shows that the properties of the ALN film remains consistent, but small fluctuations start to appear. The final observations, of course, on the 8-inch wafer. This shows that the properties are still consistent, but some area on the edge of the wafer has a lower quality compared to the center area. But we can still use more than 85% of the wafer for the next device fabrication. Then, if you are still curious about what exactly happened behind the plasma ignition process, especially when we vary the rotation speeds, this figure can give you the illustrations of the atom flux in the chamber. You can see here that the best condition is in region 2, where the rotation is balanced between target and substrate, resulting a better film uniformity and crystal quality. Now, we are almost finished. So, to summarize all of this talk, the 10% RPM rotation setting produces the most uniform and highest quality ALN film. Then, the uniformity study shows that the ALN film has a consistent film properties across the wafer, and it's very promising to proceed with further device fabrication. This is the example of the ALN film on the 8-inch silicon wafer with a customized thickness that our collaboration partner usually requests for their device fabrication, such as for high electron mobility transistors or HEMT, or even for thermal management device applications. Related to the technology readiness, this ALN thin film achieves TRL5 and contributes to the Sustainable Development Goals number 9 and 12. So that's all from me. Thank you for your attention and see you at the next lecture session.
Boleh dengar? Okay, thank you very much for your presentation. It's good presentation on the aluminum nitride sputtering. Okay, I just want to ask one question. How you measure the thickness of the thin film?
Okay, Thank you for the question. So for the thickness measurement, I have used two types of measurement. So the first one, I have used surface profiler. So during the deposition, I make a stack. So the different thickness, that's the working principle of the surface profiler. And it's not only that, I also confirm again about the thickness using the second method, which is filmetric. When using filmetric, we use the reflectance of the light interaction. And during these two types of thickness measurement, I have obtained the similar and also consistent results.
Could you please explain what are the most challenging part in terms of depositing the aluminum nitrate?
Thank you for your question. So far, the challenging part during the deposition process of the aluminum film is about maintaining the stability process. Because when we flow the nitrogen gas to the chamber, sometimes the pressure is not meet the threshold or the limitation. So to overcome this issue, usually when I want to make ILN film, I will check the gas pressure first of the nitrogen. After all of the requirement is met for the process, I will start the process.
Okay, hi Nabila. Hi Natasha. Okay, from my part, I would like to know how did you ensure the uniformity of your coating? Is it through surface roughness or through the thickness measurement? And if through the thickness measurement, how many points that you take on the surface?
Okay, thank you for the question. Okay, so for the uniformity class, I will divide the wafer into certain area. For example, for 2-inch, I will divide the area into each point because the 2-inch is considered as a small wafer. And for the 4-inch and also 8-inch, I divided the wafer into 16 area. Why they have a similar point? Because during the XRD measurement, the depression of the width is also similar. So in my opinion, it's not a big deal when we use a similar point. And then for the uniformity aspect, we consider about the color thickness, surface roughness, and also crystallinity aspects. And we also consider about the resistivity and conductivity aspects. Because when we want to deposit and also utilize all of the area of the wafer, of course, all of the surface needs and must have similar or consistent properties.
Okay, Assalamualaikum. How does the substrate temperature affect the film quality?
Okay, thank you for the question. So that's the limitation of my study for this project, because during the deposition process, I just use only room temperature. So that also become my novelty of this research, because previous study, most of the researchers, they were clear that when we want to achieve highly crystalline 002, we need to use high temperature, at least 400 degrees. So that's my novelty, because when I use only room temperature, I already achieve highly 002. But of course, I still need to observe further regarding what will happen when we introduce heating treatment during that process that I already achieved 002. So for the current study, I just use only room temperature, but for further exploration, I need to try as well for the heating treatment station.
Okay, thank you very much, Miss Natasha Sabila.
Thank you.
Thank you, Natasha, for such an inspiring presentation. Next, our second contestant We now invite Mr. Loh Kai Zwandeni to present his presentation entitled Metallurgy and Introduction. Please welcome.
Nama saya Lokashin Dedi, nombor mesin AW Auto 40118. Presentation saya bagi competition ini adalah Metallurgy, Production of Metal. Apa itu metallurgy? Metallurgy adalah satu branch study of material science regarding the properties of metal, production of metal and extraction of it by using any methods of it that can lead high productivity industrially. Boleh lihat, metallurgy adalah kajian tentang metal, production metal dan sebagainya. Contohnya, production metal, kita menggunakan blast furnace ataupun apa itu blast furnace lah. Tu blast furnace, dalam tu dia ada magma, ada heat, boleh leburkan metal itu untuk keluarkan dia punya impurities untuk dan spraykan mereka. So kita boleh dapat pure metal. Okay, ni proses extraction of metal daripada ore, dari mining kepada metal compound yang dalam bentuk powder, dia dibentuk daripada liquid dan akhirnya dia dijadikan metal dengan menyejukkan metal compound itu. Okay. So brush involved, kita ada electrochemical engineering, kita ada mechanical engineering, tambahnya lagi lah. Boleh lihat dalam zaman sekarang metallurgy atau metal untuk analytical yang guna metal seperti surgery guna electrolysis dan EV electrochemical vehicle, electric vehicle yang memang popular dalam zaman sekarang. Dan ni cara dia yang sekarang kita boleh lihat ni di sekeliling kita dalam shopping mall, dalam R&D, sistem R&D di highway dan sebagainya. Ni metode yang berkaitan dengan metallurgy lah. Ada molding untuk mewujudkan metal seperti gambar yang ada satu body yang dia tuangkan yang warna oranye tu metal yang dipanaskan dalam suhu yang amat tinggi, 100 degree Celsius. Di roll forming untuk meratakan metal, jadikan dia metal plate. So boleh buat produk-produk. Dan di contoh proses yang berkaitan dengan metallurgy, macam mana metal itu dihasilkan di industri. Sekarang kita perlu tahu apa itu metal dan non-metal. Untuk detailkan apa metallurgist buat dalam tes satu metal, dia punya properties apa. Boleh lihat metal, dia form ion, dia adalah metallic luster, dia good conductors, reliable and ductile, high melting point, more solid at room temperatures, and sonorous. And non-metal adalah lawan dalam metal, dia form anion, ion negative, dull colorless to colorful, poor conductors, brittle, low melting point, often liquid or gaseous at room temperatures, and not sonorous. Ni contoh yang metallurgist sentiasa buat untuk testing properties method itu. Boleh lihat kat sini ada hydraulic press. Yang dalam tu ada pressure sensor, displacement sensor. Dan kita ada testing machine yang activatekan load cylinder yang dalam hydraulic press tu lah. Dan kita ada control box, kita ada MCGS configuration software, kita ada control center lah, yang tapak apa-apa data yang ditapak dalam ni kita boleh dapat dalam control center. Sekarang is clear about metal properties now, but where these things come from for the metals that we use in daily life. Original form of metal. Metal seperti yang saya cakap kat muka surat pertama. Ore itu dia daripada mining, dijadikan metal compound dan akhirnya diekstrak jadi metal. Diekstrak dan disejukkan lah, jadi metal. Dan metal itu dia punya original form dipanggil ore. Ada banyak yang ikut reactivity series kalau ingat kimia, yang ore yang exist in the nature seperti bauxite, monazite, aluminium oxide dan sebagainya, dia bentuk macam kristal. Dia ada berbagai bentuk sebab yang ore itu dia dihasilkan oleh bumi dengan proses-prosesnya, proses-proses geologi lah, yang pernah belajar tentang geografi, apa itu gerakan jisim, gerakan apa-apa lah. Proses-proses geologi itu boleh hasilkan ore yang kita boleh ambil untuk buat produk. Dalam pembuatan produk, bukan saja produk metalik. Pembuatan produk kita ada dua jenis. Satunya cradle to cradle life cycle of the product, iaitu yang produk itu dia dikitas semula dan daripada sumber dua-dua lah. Dikitas semula tu yang previous consumer guna dan buang kita semula, dan ni juga boleh digunakan untuk recycle. So lepas itu kita ada pembuatan daripada natural product atau recycling product. Dan lepas produk itu dihasilkan, dia diangkut kepada rumah consumer untuk bagi consumer guna. Dan lepas consumer guna, dia dilepus. Dan yang kedua adalah cradle to grave life cycle of the product. Macam tadi tu cradle to cradle life cycle, tapi ini cradle to grave life cycle. Apa perbezaannya? Adalah yang produk itu lepas consumer tu, previous consumer tu guna, dia dilepas dan tapi dia tidak dikitas semula. Ada benda yang tidak boleh dikitas semula kan, seperti sampah plastik. Plastik itu tak biodegradable dan dia tidak boleh decompose. So dia direbut lah macam ni. So bagi metallic product, processing of metallic product adalah seperti step yang di bawah. Yang pertama mining, yang kedua extraction. Boleh lihat extraction tu contohnya rela bagas. Ya, rela bagas bahasa Melayu dia, blast furnace bahasa Inggeris. So ni proses macam mana metal itu diproseskan dan akhirnya jadinya produk. Dalam sini kalsium sedikit dan dalam hasil rela bagas yang kita buangkan metal di rela bagas tu, dia ada dua hasil. Satu pure metal, yang kedua kita panggil slag dalam bahasa Inggeris, sangga dalam bahasa Melayu lah. Sangga itu dia impurities of metal. Boleh lihat sini, since molten slag is less dense than molten iron, the slag will flow up on the top of the molten iron. From time to time, the molten slag is shred off and used to make the base of buildings and roads. So yang impurities tu dia digunakan dalam buat building, buat jalan dan sebagainya lah. Kat sini ada satu eksperimen yang amat menarik yang berkaitan dengan extraction of metal. Kat sini kita ada filter paper folded into the cone dan dalam tu ada aluminium dipanggil thermite mixture, dan kat bawah kita boleh lihat ada water layer dan sand layer di sana satu pika. Proses tu panggil thermite reaction. Kalau intos blocker yang iaitu metal plate itu dia dipanaskan, dia akan react dengan thermite mixture tu. So akan ada produk yang alih ke bawah pika lah. Manufacturing in factory adalah seperti molding yang saya tadi sebut, dan ada plaster casting process yang support sand itu dia boleh contaminate yang molten metal itu dengan heat. Dan akhirnya marketing. Metal itu dihasilkan, dijual dalam market. Environmental issues. Ya, boleh lihat seperti yang gambar ini ditunjukkan adalah kes garam patah Sungai Kingking pada 2019. Boleh lihat yang batuan itu dia jadi kotor, dia jadi hitam macam tu. Asalnya dia warna putih. Saya tak boleh cari apa asal dia. Tapi ini lepas dia dipollute oleh river di Sungai Kingking yang ada mercury. So dia jadi macam ni lah. Ni yang saya dapat daripada satu artikel Science Direct, Making Sustainable Aluminium by Recycling Scrap. the size of 30 alloys. Aluminium memang adalah satu 30 alloys yang dia di-extract melalui electrolysis. Tapi masa aluminium di-extract, ada impurities dia yang memang sangat poisonous, sangat non-eco-friendly. So, kita perlulah recycling aluminium lah. Contohnya, tong recycle. Ada 3 kan. Salah satunya yang warna coklat adalah aluminium lah. Aluminium can. Ini processing aluminium. Dan yang tu adalah satu furnace yang special yang digunakan dalam industri untuk processing metal. So, molten metal aluminium akan paling gelap lah. Paling gelap untuk disejukkan. Nah, ini dia. Nah, ini untuk dapatkan acuan dia. So, dia ada bentuk lah. Dia jadi solid. Nah, ini hasil metal yang dia buat. Moral values, love our love, use more sustainable method. Ini reference saya. Terima kasih.
Okay, thank you very much. Low Kaizwan Denny, is correct? Okay, you can hear me? Okay, thank you very much for your presentation. I just want to know what is normally used for the metal testing, the common testing for the metal.
Common testing, such as mechanical stress testing, or what chemical testing, or so on.
I can hear you. What is the normal or common testing for the metal?
Stress testing.
Thank you.
Okay. During the extraction of iron using the blast furnace, what is the maximum temperature of the operation?
1000 degrees.
One thousand, okay.
Hello. Anthony, do you hear me? Hello. Hello, test. Okay, Lau Kai Zuan Denny. First of all, I would like to congratulate you because for participate in this lecture competition. So from my part, I would like to ask you about is there any lack or is there any decrement of properties when we recycle that materials?
Yes. Can repeat the question?
Is there any lack of the material compared to the origin materials when we recycle of that materials? How does is it any difference between original material or virgin material with recycled material? What is your opinion?
I think the original material, they have different properties to the recycled material because original material they cannot be recycled because they are not well degradable. Yeah, that's my answer.
Okay, hi Danny. What is the difference between metallurgy and steel? What is the difference between metal and steel? Do you have any idea?
Metal is a form of element. Steel is a form of alloy. That the metal is inserted some impurities, so it becomes an alloy.
Okay, Danny, thank you very much for your presentation. Okay.
Thank you.
Thank you, Denny, for such a wonderful presentation. Next, our third contestant. Please welcome Chua Yi Heng with his presentation entitled Growth and Characterization of Zinc Oxide Nanowire on Dye-Sensitized Solar Cell. Please welcome.
Very good morning to all judges. I'm Chua Yi, and today I'll be discussing both growth and characterization of zinc oxide. Is the table then? Wait, so before I start, the judges heard news that Malaysia is introducing a new tariff electricity where starting from 1st of July, and society is debating whether the market price will go up or not. But the border of the picture is very clear, which is not only Malaysian but a global energy crisis. This is because as population grows, so does demands, urging the needs of sustainable energy. Yet our sun, it delivers 3 times 10 power of 24 joules of energy per year, which is around 10,000 times of the current global consumption. Imagine even we tap even a fraction more efficiently. Thus, I can say that the solar energy has a vast potential in the future. So, in harvesting solar energy, many inventions of solar cells have been made, such as crystalline silicon, thin film, perovskite, and many more. And DSSC, also called dye-synthesized solar cell, which is the topic of my title. It's a type of thin film solar cell. It's created from abundant and inexpensive material, and used in portable electronics and IoT due to its lightweight, thin, and flexible characteristic. The DSSC consists of a light-absorbing dye, an electrolyte, a working electrode, which is a positive, and a counter electrode, which is a negative electrode. While the TiO2, also called tin oxide, acts as a semiconductor in DSSC for transporting electrons. But for your information, zinc oxide can be as an alternative of tin oxide, as its band gap and electron affinity are almost the same. Crucially, zinc oxide offers a much higher electron mobility, which in principle enables faster charge carrier transport and less recombination, while its nanowire structure can provide a direct pathway for electron transfer and significantly faster the electron transit, thus making zinc oxide nanowire an attractive material to be explored in DSSC. However, Zinc oxide nanowire and DSSC also possesses challenges that need to be addressed. The main problem that is its efficiency is quite low, which is around 15.2 at maximum, created by Muchiwani at 2005. And other problems like reproducible growth and defect control of zinc oxide nanowire, which is due to the lattice mismatch. Lastly, is the fine-tuning of the electrical and optical of zinc oxide nanowire. Thus, fine-tuning the ratio of aluminium atomic percentage in aluminium zinc oxide nanowire is crucial for achieving the above stages and maximizing the performance. Most of the research paper covers 0.5, 1, 2, 3 of atomic percentage of the aluminium, and has found that 1 atomic percentage shows the optimum zinc oxide nanowire properties. Hence, in this research work, the investigation of the aluminium doping will be centered around 1 atomic percentage of aluminium for fine-tuning. The purpose of fine-tuning is to discover a new process-structure relationship and the sweet point for the maximum electrical and optical properties of aluminium-doped zinc oxide nanowire in DSSC. So my title is mainly focused on to synthesize the zinc oxide thin film as a seeding layer using magnetron sputtering, and to growth and characterization of zinc oxide nanowire as aluminium dope, and lastly to analyze the structural, electrical and optical properties of aluminium doped zinc oxide nanowire growth on the zinc oxide thin film. So for the scope of study, the intention is to yield zinc oxide nanowire by reviewing up-to-date condition via RF sputtering seed layer, hydrothermal growth and controlled aluminium doping to achieve vertically aligned nanowire arrays, while characterization of the morphological, electrical and optical will be done, and the data will be compared to the previous research for further scaling. So, this study is significant as it discovered the existence of a new process, structure and property relationship by fine-tuning the aluminium percentage. And the research of zinc oxide will have the industrial lessening its dependence on rare material and cutting down the costs, leading to a hand in the transition to a sustainable energy source. So the two is the literature review. So as you can see, this table is summarized the finding of previous research on zinc oxide as an alternative, and found out why nanowire exhibit high electrochemical coupling, and the reason why we choose the hydrothermal as the synthesis method, and it was explained by Guo at 2019. Next. Okay, for the hydrothermal parameter, I also have been review many of the articles and found that to achieve a vertical aligned zinc oxide nanowire, we need like increasing in growth temperature that will be resulting increase in transmittance and decrease in resistivity by Muchiwani at 2017. And Major Gracia found that 1% of atomic percentage of aluminium has the highest intensity and transmittance compared to other sample like 0.5 atomic percentage and 2 and 3 of the atomic percentage of aluminium. Other like sputtering parameter, I will be briefly explained during the methodology part, and proceed to the third part, methodology. In depositing the seed layer, radio frequency magnetron sputtering will be used. Firstly, fluorine tin oxide will be sputtered at 80 watt for 1 hour using 30 to 50 nanometer zinc oxide film, and the gas flow will be controlled at around 25 standard cubic centimeter per minute for argon and 1 SCCM for oxygen, and around 1.3 Pascal of pressure will be used to minimize the oxygen vacancy. After that, post-handling will be done at 350 degrees in air for 1 hour to improve the crystallinity. Next, hydrothermal growth will be done by mixing hexamethyl tetramine with zinc nitrate hexaderide for equimolar concentration of 0.025 mole, balancing the dye loading with efficiency of charge transport. The mixture is then added with aluminium nitrate monohydrate to yield around 0.9 to 1.2 atomic percentage and put inside the autoclave. The atomic percentage is calculated through the molality of the substance, and the autoclave is then placed in the oven to heat for around 90 degrees and 9 hours. So, and this is the flow chart of the whole procedure. Okay, firstly, as you can see that first I will sputter my thin film, which is zinc oxide of purity of 99.99 on a FTO substrate, and hope that it will deposit uniformly. And I'll proceed to the next one, which is the hydrothermal, and which is I will use a different atomic percentage of aluminium to dope the zinc oxide nanowire and make sure it grows vertically aligned. And I will characterization it with XRD, SEM, and EDX. And if the sample has a uniform morphology, then I will proceed to the last characterization, which is the optical and electrical characterization. And finally, I can get my results. The uniformity of the thin film will be checked first before proceeding to the hydrothermal, and the XRD, SEM, EDX will be done first before investigating the electrical and optical properties, as the morphology of zinc oxide directly influences properties. Proceeding to the characterization technique, firstly is the SEM, or so-called scanning electron microscope, which is used to verify nanowire alignment, aspect ratio, uniformity, and guide the growth optimization. And next is the energy diffusive X-ray, XRD, which is used to examine presence and distribution of aluminium or other dopants and check purity of the stoichiometry of nanowire. Next is the XRD diffraction, which is used to confirm reside zinc oxide nanostructure, C-axis alignment, effect of doping on crystal quality. And next is the UV-Vis, or so-called ultraviolet spectroscopy, which is used to record transmittance percentage across the visible wavelength. And lastly is the 4-point probe, which is used to calculate the zinc oxide resistivity. And after that, we can use to calculate the figure of merit for the zinc oxide nanowire thin film. Next, the chapter 4 expected result. So as you can see that the dense forest of vertically aligned nanowire on sparse layer with a diameter of 50 to 100 nanometer uniform spacings, and this cross-section view shows perpendicular growth and consistent alignment. So here's a more detailed view, as you can see. Okay, so next for the XRD analysis. As you can see that the sharp zinc oxide peaks with dominant 002 reflection near 2 theta 34 degrees and have a slight shift for an undot. So it's predicted that from a 0.9 to 1.2 atomic percentage, the shift will be very slightly to be observed. And next for the EDX analysis, as you can see that clear zinc oxide K alpha and oxide K alpha peaks, where the aluminium also have a K alpha peak corresponding to the target and for 0.9 atomic percentage. Next is the UV-Vis analysis, or so-called ultraviolet visible spectroscopy, which is used to determine the visible range transmittance. So the up one is the difference between undoped and doped for a coated FTO, and while the bottom one is for the plastic but with atomic percentage difference of 0.5 to 3%. So for my investigation is a bit similar like the bottom one, but their difference might be slightly. And lastly is the 4-point probe analysis, which is used to examine the resistivity of zinc oxide nanowire, and will be plotted into a figure of merit, which is used to balance between the resistance and the transmittance of the substance. And this is the sum of the reference I've been used in my title. So, as a conclusion, this presentation it outlines a comprehensive plan to develop a characterization of vertically aligned aluminium doped zinc oxide nanowire to use for as a transparent conductive photoanodes in a dye-sensitized solar cell. So, by combining RF sputtering of zinc oxide seed layer with low temperature hydrothermal growth and precise tuning of aluminium doping between 0.9 to 1.2 atomic percentage, this study will establish a reproducible synthesis protocol for high-quality zinc oxide nanowire with controlled morphology and alignment. So, I will correlate the doping levels with structural XRD, compositional EDX, and optical of UV, Vis, and electrical of 4-point probe properties. And I will identify the optimum aluminium concentration, which will be predicted around 1.0 to 1.1%, that maximize the transparency, conductive trade-off as quantified by a peak figure of merit. So, achieving these goals will demonstrate the feasibility of a low cost of abundant aluminium doped zinc oxide nanowire, and this insight gain will lay a solid foundation for virtual device fabrications and performance testing, ultimately contributing to more sustainable and scalable solar technology. So that's all for me. Thank you.
Okay, thank you very much. Chua Zi Heng. Okay, thank you. And then that's good presentation. I just want to know, you already done for this one for experiment?
Haven't yet.
And no, haven't yet. Okay, so that's why I see the SEM that look like from the other people. So actually, when you want to say the nano wire, so you need to describe the nano wire. Okay, what is actually the aspect ratio for the nano wire? You doesn't know.
Sorry, can you repeat the question?
Aspect ratio.
Aspect ratio of nanowire. Aspect ratio in terms of with.
Yes. Yeah, because of the wire, they have the length and also they have the diameter. So when we want to say that it's wire, so they have the characteristic for the wire. That is not like whiskers or just a rod, because wire is different with the rod or cylinder. Because on your presentation, you have the aspect ratio there. You put there for the characteristic. You aware or not?
For the aspect ratio of the characteristics.
Yeah.
You mean, sorry.
Okay,
is it, which characteristic?
It's possible to see your. It's possible to see your slide now.
Yes. With,
on the presentation, because you state there about the aspect ratio, so it looks like you not understand what is the aspect ratio. Okay, if you not understand, you can go and then you see that what is aspect ratio, because we want to classify as the wire, so there is to have the certain characteristic for the wire. Okay.
Okay.
Okay. Okay. Thank you.
Okay. Good morning, Chua Yihan. Okay, I have a very basic question. Prove that zinc oxide is a ceramic.
Zinc oxide is ceramic.
Okay. Prove that zinc oxide is a ceramic.
Zinc oxide can be a ceramic in terms of because it is a semiconductor. Because actually he also exhibit high temperature stability, and he has a thermal conductivity, and so it can be used as a ceramic also, and like it can be used to protect for electronic circuits, and and its microstructure also can be tolerated for specification in the ceramic processing. For the zinc oxide base of the ceramic, it can use, if I'm not mistaken, zinc oxide based ceramic nanofibers can be used in sensors and fuel cells and other applications.
Okay, hi Chua. Okay, so when we talking about or when we discuss about a solar cell, so as we know, solar cell have its service expiration, or after certain years, the solar cell will be decreased its performance. So, in your opinion, based on your findings and your review, does zinc oxide nanowire had influence, or is it that material also have any expiration? Please advise. Thank you.
Because for my research, zinc oxide nanowire in this case, it only exhibit more fast carrier transports and maybe like a higher electromobility, but it doesn't really affect the lifetime of the DSSC. So if I'm not mistaken, the lifetime of DSSC is more to the electrolyte, which is also my limitation because I didn't touch up the electrolyte part. I just touch up the semicon part. Yes. So for my study, implementing the zinc oxide doesn't really affect the lifetime of the DSSC.
Hi Chua. Okay, how does the dimension of nanowire affect the performance of your DSSC?
Dimension.
In the length, the size, the diameter, how is affect
Okay. So I'm expecting to yield a diameter like around like 50 nanometer for like a very has a how to say a very good like more stable, doesn't it its length doesn't exceed like 18 nanometer or very short like 20 nanometer. It will like be an average for what I expected to be yield to serve as a balance between the axial and radial growth for the hydrothermal, and which I will, if I balance between the diameter and the length like around in the average, it can apply in many applications also, which is suitable for suitable for the zinc oxide. So in my case, I will tend to yield an average diameter for 15 nanometer.
Very much for your presentation.
Thank you.
Okay, thank you Chua for such an excellent presentation. Our fourth contestant, next we have Miss Saraswati Anak Perempuan Velaitam with her presentation entitled Effect of Calcination on Crayfish Shells. Please welcome.
Hello and good day to the judges and audience. I'm Saraswati Velaitam from University Tun Usin on Malaysia, and I'm honored to present my research titled Effect of Calcination on Crayfish Shells. Today, I will walk you through how we can turn environmental nuisance into sustainable value. Crayfish, specifically Charax quadricarinatus, are freshwater crustaceans with a high shell-to-flesh ratio, which is about 80 to 85% of their body is shell. Globally, more than 100,000 tons of crayfish are consumed each year. In Malaysia, this species has been characterized as an invasive due to its rapid reproduction and potential to disrupt local aquatic biodiversity. Improper disposal of their shells contributes to waste buildup, pollution, and methane gas emissions. During my visit to a site in Parit Sulon, Johor, I observed how fast they can breed and how they must be frequently caught. While some are consumed, most of their shells are discarded. And that's where I saw an opportunity. The poor management of crayfish waste leads to environmental issues. The shells are often discarded without proper treatment, attracting pests, releasing unpleasant odors, and emitting methane as they decompose. This research aims to address both waste from invasive species and environmental pollution by converting discarded shells into reusable material. This research is guided by the following objectives. Number 1, to calcine crayfish shells at 550, 600, 700 and 900 Celsius. To characterize raw and calcined crayfish shells and to analyze the microstructure of raw and calcined crayfish shells. Crayfish shells are primarily composed of chitin around 20 to 30%, protein 20 to 30% and calcium carbonate around 30 to 40% of the shell. These biocomponents are valuable, particularly the calcium carbonate, which through calcination decomposes into calcium oxide and release carbon dioxide. Calcium oxide is a highly reactive compound with strong basic properties, making it valuable in neutralizing acidic waste and capturing heavy metals in contaminated water. To investigate this potential, the research involved few steps, which is collecting crayfish shells from a local source, and then clean and dry them at 90 Celsius for 24 hours in the oven. After that, grind them into a fine powder and sieve through a 63 micrometer mesh. After that, calcine the powder at 550, 600, 700 and 900 Celsius using a muffle furnace. Finally, characterizing the raw 550 Celsius and 600 Celsius samples using XRD, FTIR and SEM. The SCM image of raw crayfish shell powder shows a compact and layered surface structure. SCM EDX also confirmed the presence of key elements like calcium, carbon, and phosphorus. This initial structure serves as a reference to observe how morphology changes after calcination. XRD patterns indicate the beginning of calcium oxide formation at 550 Celsius. At 600 Celsius, calcium oxide peaks become more pronounced, confirming partial decomposition of calcium carbonate. Further improvements and complete conversion are expected at 700 Celsius and 900 Celsius, which are planned for future analysis. FTIR spectra revealed strong carbonate bands in raw samples, which began to diminish at 550 Celsius and further decrease at 600 Celsius. New oxide-related functional groups began to appear at 600 Celsius, confirming the onset of calcium carbonate decomposition. At 550 Celsius, the powder turned dark grey due to the presence of residual carbon. At 600 Celsius, the color lightened, indicating organic matter burned off. These changes visually support the findings from XRD and FTIR. Why is this important? Calcium oxide derived from crayfish shells can be applied to remove heavy metals from wastewater. When calcium oxide is added to water, it forms calcium hydroxide, which increases the pH and promotes the precipitation of heavy metal ions like lead, cadmium, and copper. These ions bind to hydroxide groups or settle out as insoluble metal hydroxides, effectively removing them from the water column. This research is not only about chemical conversion, it contributes to broader goals. First one is waste reduction and management. Development of cost-effective environmental solutions. And then reduction in water contamination, turning invasive species waste into a sustainable resource. This research supports the following sustainable development goals. First one is Sustainable Development Goal number 6, clean water and sanitation. And then SDG 12, which is responsible consumption and production. And then SDG 14, which is life below water. By transforming invasive species waste into valuable materials, this project aligns with sustainable development and circular economy principles. To build on this work, I plan to complete XRD and FTIR tests for 700 Celsius and 900 Celsius samples, and then conduct adsorption tests using real wastewater, and then optimize calcination parameters for maximum calcium oxide formation, and then evaluate regeneration and reuse potential of the material. After that, benchmark crayfish shell against other marine bio-waste materials. In summary, this study demonstrates that crayfish shell waste, which is often discarded, can be transformed into a calcium oxide through calcination. The resulting material is not only valuable for heavy metal removal, but also aligns with green and sustainable engineering practices. With further development, this could become a low-cost solution for wastewater treatment across industries. I would like to thank my supervisor, and then UTHM, University Tun Usain on Malaysia, the lab technicians of UTHM, and the organizers of MLC 2025 for this opportunity. Thank you for your time and attention.
Okay, thank you very much for your presentation. And I think I cannot give the comment because in your presentation, you show me in your presentation, so I give to my members to comment about your presentation.
Okay. Good morning, Saraswati. In your work, you have mentioned that the calcination temperature starts at 500 degrees Celsius, correct?
500.
Yeah, 500 and up to 900 degrees Celsius. Basically, the reaction temperature for calcium carbonate into calcium oxide occurs basically above 700 degrees Celsius. So what is the purpose of having lower temperatures? Because obviously there will be no reaction happens at that particular temperatures.
Okay, thank you for the question, sir. Most literature reports that 700 Celsius is the optimum temperature for calcination for crayfish shells. But I choose the 550 and 600 Celsius to observe the early stage thermal decomposition, and 900 Celsius to see the higher maximum decomposition stages and observe the changes. Because we can see the changes of calcium oxide levels in 550, 600, how it increases. So that's why I choose the less temperature.
Hi Saraswati.
Yes,
Okay, my question is there any other potential application for your crayfish powder?
Besides, it means beside the wastewater treatment, is it?
Yeah.
Mostly other crustacean cells can be used for wastewater for heavy metals, not only for heavy metals, for dye absorption, and also as a can combine with can use for civil construction methods. It can combine with cement to form a strong foundation for buildings.
Saraswati.
Hi Saraswati. Since Professor don't ask any questions, so can I ask you two questions? First question is, what is the main purpose of calcination? And the second one is, what is the chemical transformation during the calcination? Thank you.
Thank you, Doctor. For the main purpose of the calcination is to get the calcium oxide from calcium carbonate. So the chemical reaction is when we heat, the calcium carbonate turn into calcium oxide and releases carbon dioxide. We just want to get the calcium oxide to do the wastewater treatment.
Okay, thank you.
Okay, thank you very much for the presentation today. Okay.
Debating presentation. Now we go next to our fifth contestant. Please now welcome Mr. Ahmad Fathan bin Ahmad Fazuli with his presentation entitled "The Property of Electrolyte Solid Oxide Fuel Cell by Adding Sintering Aid of Risa Silica into Samarium Ceria for Lowering the Sintering Temperature." Please welcome.
Assalamualaikum and good morning to honorable judges and fellow participants. My name is Fathan Fazuli. I would like to explain about my project entitled The Property of Electrolyte for SOFC by adding sintering aid of rice husk ash into samarium ceria to lowering sintering temperature. Let's dive into problem statement. As we know, Malaysia's agriculture annually produces approximately 0.48 million tons of rice husk waste. Unfortunately, most of them were burned openly, which cause pollution, and we technically neglect the potential of recycling this material to strengthen SOFC structure. Second is higher sintering temperature required for SOFC fabrication, which will cause micro cracks. And then next, objectives study. First is to fabricate SOFC electrolyte using rice husk ash as sintering aid at different weight percentage to characterize and fabricate solid oxide fuel cell electrolyte of SDC RHA for physical, chemical and morphological properties, to study the influence of RHA weight percentage towards sintering temperature. For the scope of study, first, raw rice husk is heated to 700 Celsius for 4 hours to form rice husk silica. The key sintering aid in the study is to produce pure rice husk silica. And next, we mix the RHA with samarium ceria at precise ratio of 99.5% SDC, which means another 0.5% RHA, and other composition is 99% SDC with 1% RHA. It's actually like a recipe. If we put too little rice husk, it won't have a significant change, but too much would weaken the electrolyte. So basically, we are testing the perfect balance between both. The mixed powder is then compressed into pellets under 3 tons of pressure for 3 minutes. This ensures uniformity and density, which replicating real-world SOFC manufacturing condition. Then the pellets undergo sintering at 4 critical temperatures, which are 900, 1000, 1100 and 1200 Celsius. Finally, RHA SDC will be analyzed with physical, chemical and morphological properties. Okay, let's dive into literature review. First and foremost, imagine a device that generates electricity without burning fuel, no smoke, no pollution, just clean energy. That's the magic of solid oxide fuel cell. SOFC is high-tech electricity generator. It uses hydrogen or natural gas. Instead of burning them, it creates electricity through a chemical reaction, which is induced electron, making it super efficient and great eco-friendly energy. It's actually like a battery that never dies as long as you keep feeding it with fuel and air. Inside every SOFC, there are 3 layers, which are anode, where fuel goes in, cathode, where oxygen comes in, and electrolyte, where the medium to conduct oxygen ions to create induced electron. SOFC operates at scorching temperature up to 1600 Celsius. That's hotter than lava, but this extreme temperature is the main challenge in SOFC operation, which costs a lot of money and can damage material over a long time. Now, what is SDC and how it is used in SOFC? If SOFC are future of clean energy, then SDC is the secret sauce that makes them work better and cheaper. SDC is a next-gen electrolyte. It works at lower temperature, around 500 to 700 Celsius. My project, I'm making SDC even better by adding rice husk silica to cut those temperatures further. Lower temperature aren't just convenient, they are triple twins. First, less material degradation. Second, cheaper heating costs. And third, faster startup times. No need to wait for temperature rise at extreme heat. And that's where my project comes in, by adding rice husk silica into SDC, which is expected to push those temperatures lower while maintaining its current efficiency. Okay, this is the main testing. SRD scan angle from 10 degree to 80 degree at 1000 Celsius to 1200 Celsius. Why this temperature is selected? Because previous research, they said that this range of temperature are sweet spot where expect cubic fluoride phase formation for oxygen ion conduction in SDC, which is essential to produce electricity from induced electron. For TGA, previous paper used 1000 to 1200 Celsius. Each step reveals how RHA influence SDC behavior at different temperature, helping us to find the lowest possible temperature without sacrificing performance of the electrolyte itself. It's like baking a cake. If too low temperature, it's raw. Too high temperature, it will burn. We are finding the perfect recipe. After sintering for 4 hours, we measure density via image processing. For our target is the density supposedly tolerance of plus minus 5 to 6%. For methodology, for RHA become sintering aid, it needs a transformation. RHA is burned at 700 Celsius for 4 hours at heating rate 5 Celsius per minute using furnace. Why we choose 700 Celsius? Because based on previous study, at this temperature, the silica content is in amorphous state, so it is highly purity. This step convert rice husk ash into high purity amorphous silica, which is the active element needed to enhance SDC sintering. Calcination also burns moisture and organic contaminants, leaving behind pure functional silica. Same process. We use planetary monoamine with ratio 20 gram of electrolyte with 20 pieces of zirconium bar. In the fridge jar, we set 200 rpm for 3 hours duration. It's long enough to achieve a fine and uniform powder. We're afraid if more than 3 hours, the fridge jar will overheat the materials and affect the properties. At 200 rpm, it's enough for zirconia balls to strike the balance between fracture energy and avoiding agglomeration formed in the electrolyte. Okay, next, we move to savings. First, electrolyte is crushed finer using agate mortar. Why agate? Because it's hard and chemically inert, so it won't contaminate our sample. Next, we pass the powder through a 60 micron mesh using vibration screener for 10 minutes. This filter out larger particles which are more than 60 micron, so ensuring it's only the finest particle left. Let's go to pelletizing. As DC RHA pelletized into chunk of cylindrical pellet, and its average weight is about 0.5 gram, 1 millimeter thick, and 13 millimeter in diameter more. The samples are pressed uniaxially under 3 tons for about 3 minutes. The process will be monitored start and end degradation curve. The sample is then placed in the furnace at 900 Celsius, 1000 Celsius, 1100 Celsius, and 1200 Celsius for 60 minutes. The heat rate is 5 Celsius per minute. This is the sintering profile, as you can see, because we need to determine at what time and cycle. Next, we go to result and discussion. TGA. For TGA, data reveals a clear pattern. Higher temperature cause greater weight loss in electrolytes, while testing stopped at TGA data reveals a clear pattern. Higher temperature cause greater weight loss in SCC RHA, while testing stopped at 1400 Celsius due to equipment limits. The critical degradation window from 900 Celsius to 1200 Celsius is fully monitored. Why does this happen? At high heat, Serbia-based materials undergo phase transition that distort crystal structure, leading to mass loss. And this change also lead to increasing in porosity. Here's where silicon from RHA becomes a game changer. It stabilizing the structure, modifies crystallinity, potentially lowering optimal sintering temperature and reduce oxygen loss, and also preserving ionic conductivity for SRD. Here's what SRD reveals. At 900 Celsius, as we can see, quartz phase detected. At 1000, 1100, and 1200, there is tridymite and also crystalline phase. For ICM, this same image revealed that each sample was taken at 3 different spots. For each composition at same temperature, the image show almost similar microstructure. There's a lot of white spot, black spot. Okay, as you can see, at 99% SDC at 900 Celsius, there's scattered small pores like Swiss cheese, and also agglomeration particles at 1200 Celsius. Pores become larger but fewer. Particle is homogenized. This shows that RHA promote its densification while manage pores distribution. For 99.5%, left hand side, at 900 Celsius, there's largest pores. At 1200 Celsius, there's unexpected reversal. More pores emerge. EDX, elemental compositions. EDX analysis reveals how temperature and RHA content orchestrate the elemental symphony in our SEC RHA composites. Let's see how the patterns. There is 2 distinct regimes. First is at 900 Celsius and 1000 Celsius. The present element is OK, CER, and SMR. At 1100 Celsius and 1200 Celsius, element is SIK. Silicon source in SIK present is slightly due to thermal decomposition of rice husk. organic nature of rice husk ash. Silica purity comes from rice husk ash composition of 1% and 0.5%. This small percentage effect amount of silica purity in SDCRHA mixture. The presence of Si will fill the void between SDCRHA and increase porosity. Okay, let's jump to porosity density. Both SDCRHA compositions show reliable porosity between 5% and 7%. Porosity range, as you can see, 99% SDC porosity is between 5.4 to 6.63. 99.5% SDC porosity between 5.77 to 6.39%. As you can see here, there's a red in cross-section SAM mesh, and this red indicates the pore of the electrolyte. Some black region in the mesh are not found as pores due to focusing issues. At high magnification of 100,000 times, which is the limitation of the machine, to capture clear instead produce blurry image. In summary, this study demonstrates that rice husk ash silica is a game-changing centering aid for SDC electrolytes. The study successfully engineered SDC-RHA composite that hit all three targets. First, fabrication, which is use RHA as centering aid across weight percentage, cost effectiveness, and performance, which made the key SOC electrolyte physical, chemical, and morphological structure only, not in terms of conductivity property because of time constraint. In short, higher silica purity demands higher centering temperature, leading to faster crystallization and dense packing, which reduce the porosity of electrolyte itself. Analogically, RHA content is like a control knob. If you want lower temperature, you adjust the rice husk, and if you need specific porosity of your electrolyte, you also need to tune the rice husk. For further recommendation, higher silica purity improve porosity and surface crystallology. To increase silica content, raise the percentage of RHA to produce more crystallized silica with SDC. For pelletizing program, an SDC RHA mixture becomes written after being pelletized to silicate tablets. PEG solution, the gel-like structure cause SDC RHA to stick inside the mold cavity. There is alternative binder such as glycerol instead of using PEG. Glycerol acts as humectant. Humectant retains moisture to prevent brittleness, lubricant, reduce mold sticking, and cost effective. And as glycerol is organic solvent. That's all from me. Thank you.
Okay, thank you very much for your presentation. Okay, it's good and then technical. This is very nice. So, actually, what you want to do is to reduce or centering aid for the SDC. Is correct? Okay. Okay, so you use this rice husk, and then you want to replace what you want to replace something, isn't it? Okay. Now I just want to go through and then see the density. How you measure density? Because when you say about the density, your slide show that the SEM image. So how you measure that one? Tak dengar. Tak dengar. Okay.
Zura Afif rasa. Zula. Tapi tajuk ni tajuk SM dia.
Budak master ni. Zula buat tajuk ni.
Tak. Itu SM dia.
Dia budak SM Jad dulu.
Kasih saya.
Oh.
Okay, boleh dengar ke?
Budak tu duduk kat mana?
Cornwall tu.
Lah.
Okay, dengar?
Okay, dengar.
Okay, basically for porosity density, I use image processing tool that measure the contrast of different dot spots. So as you can see, may I share my screen?
Okay, can.
As you can see,
Kau duduk sini jadi pegang.
there is a red spot here. A red spot indicates pores that can be seen in the cross-section. So basically, I am using the image contrast to detect the black spot and white spot. Black spot indicates that the cross-section is having pores, and the white spot is the actual space that detected.
Okay, you need to know the density is.
Detect porosity density.
Okay, you need to know that. You need to mention and describe. You use a planar density. That means 2D density. Is not density normally 3D. Okay, density about volume. That is not surface. Okay, you need to mention that there is the surface density. Okay. When we use like this, there is the surface density. It's not density. Okay, thank you.
Thank you for the compliment.
Assalamualaikum Ahmad Fatan. Okay, when converting rice husk into silica, one of the major problem is carbon. Okay, so how do you control the carbon contamination in your specimens?
Okay, how I control the carbon footprint from the fermentation of SOFC is through the what call it, calcination of certain temperature. To determine the temperature, I used to run the TGA test. So from the TGA test, I can determine at what temperature that the material is degraded. So if you can see in the TGA itself, so the mass start degrade from 900 Celsius. So basically, I don't need to test up until 1600 Celsius in order to detect the degradation phase. So that's how I control the extreme heat of doing this test.
Okay, Fathan, thank you for your presentation. So I would like to ask you on what is your opinion? How far is the use of sintering aid will reduce the cost of solid oxide fuel cell?
Okay, in my opinion, as you can see, the operate temperature of SOFC can reach up to 1600 Celsius. The heat is like more hotter than lava itself. So indeed, we don't need to achieve 1600 Celsius, but with sintering aid, we can reduce the 1600 Celsius to 1200 Celsius and below. So basically, this study is to determine, is it possible to reduce more than 1200 Celsius of operating temperature of SOFC. So I think maybe, in my opinion, sintering aid is the key player to ensure that the SOFC operation will be more efficiency and eco-friendly.
Okay, thank you, Fatan.
Thank you.
Okay, Ahmad Fatan. How the Raisa silica affect the microstructure of SDC? Thank you.
Okay, as you can see from the degradation mass, when we burn at 900 Celsius to 1200 Celsius, there is a lot, there is change in gas, 0.56 until 0.68. So this change make the SDC itself less in less, so it has void in between the structure. So the presence of silica element in the RHA is expected to fill up the void in between the particle of SDC itself. So it will increase the density of SDC itself to achieve electrolyte properties in terms of density.
All right, thank you.
Okay, thank you very much. Okay.
Okay, thank you, Ahmad Fatan, for such a well-delivered presentation. Now, last but not least, our final contestant of today. Please welcome Mr. Muhammad Syahmi Sufi Abdul Syukur with his presentation entitled Eco-Ceramic in Action, Impact of Sintering Temperature on Rice Husk Derived Water Filters. Please welcome.
Bismillahirrahmanirrahim. Assalamualaikum and a very good day I bid to all panelists and my fellow friends. So for today's presentation for MLC 2025, which is Material Lecture Competition 2025 UTHM, I will present about my research study, which is entitled Eco-Ceramic Action, Impact of Sintering Temperature on Rice Husk Derived Silica Water Filters. So for today's presentation will be presented by me, which is Muhammad Syahmi Sufi bin Abdul Syukur. And for this research study, I will be under the supervision of my supervisor, which is Associate Professor Engineer Dr. Sufi Zabri Ahmad and Co-Supervisor Dr. Fazimah Ahmad. Alright, so for today's presentation, first of all, we will take a look at the introduction for this research study, and then we will take a look at the literature review, methodology, results and discussion, and last but not least, we will take a look at the conclusion for this research study. First of all, we will take a look at the background of study for this research study. The national policy on the environment was adopted in 2002, which outlines the strategies to propel countries' growth plans towards sustainable development. Next, the silica, which also known as silicon dioxide, is an oxide of the silicon element, which is the second most abundant element found on Earth. For this research study, is aimed to fabricate the silica water filter by using the steam casting method, and then we will do the investigation on the physical properties of the silica water filter. Alright, as we all know, 400,000 tons annually of rice husk waste product will be thrown away or burned by the traditional farmers. We also know that if the paddy rice husk waste product will be burned in the open air, it will cause the release of carbon dioxide. So for controlling these problems, we will burn the rice husk waste product with 500 degrees Celsius of burn off temperature to produce amorphous silica. Alright, so for the problem statements for this research study, the abundance of rice husk today is the reason why many researchers want to study the benefits and appropriate ways to reduce the waste produced by paddy agriculture. Secondly, This research focuses on utilizing amorphous silica for silica water filters from rice husk waste product. Thirdly, silica is a basic raw material widely used in the semiconductors, ceramics, polymers, and material industries. Researchers also states that amorphous silica can be produced when burned at 500 degrees Celsius to 800 degrees Celsius, which is for the crystalline silica will be burned at 700 degrees Celsius until 1200 degrees Celsius. These are the objectives for this research study. First of all, we will take a look at two focuses to produce the amorphous silica from rice husk waste product gathered from Pasir-Tumbuh, Kelantan. And then the second objective is to fabricate the silica water filter by using slip casting method from the silica that have been produced from the rice husk waste product. Third objective is to investigate the physical properties of the fabricated silica water filter. As stated earlier, these are the scope of study for this research study. For the silica gathered from this study, which will gathered from the rice husk waste product, and then for the filler, we will take the kaolin clay. For the mold fabrication, we will use the plaster of Paris, which is POP. And then these are the scope for the amorphous silica, which is it will be burned off by 500 degrees Celsius temperature with a heating and cooling rate of 5 degrees Celsius. For the silica composition, we will take the 50, 60, and 70% of the silica. For the synchronous temperature, we will take the 900, 1000, and 1100 degrees Celsius. So, for the physical properties of the silica, we will use the phase analysis, which is X-ray diffraction, which is XRD. For the silica water filter, the physical properties that will be studied is on the morphological analysis, which is scanning electron microscopy and energy dispersive X-ray. For phase analysis, we will use the X-ray diffraction, and then the density and porosity analysis of the fabricated silica water filter. Alright, next we will take a look at the literature review for this research study. First of all, this is the cycle of sustainability for this research study, which is we will gather the rice husk waste product from Pasir-Tumbuh, Kelantan, and then we will produce the amorphous silica that will be used for fabricating the silica water filter, and then the used water filter will be crushed to produce fertilizer, and then the fertilizer will be poured again into the paddy field. Alright, these are the structure of the rice husk waste product. The rice husk waste product, which is the outer layer of the rice grain, and then we will produce the amorphous silica from this rice husk waste product. Alright, from Harun et al. 2013 states that these are the suitable sintering temperature, which is the two stages of sintering temperature for producing the amorphous silica water filter. Next, we take a look at the methodology for this research study. These are the flow chart for the silica water filter fabrication. First of all, we will produce the mold that will be used for this research study. And then, after fabricated the silica water filter, if there is any defect from the water filter, we will crush again the water filter, and then we will do again the slip casting method. If there is no any defect from the fabricated silica water filter, we will get the physical properties of the silica water filter, and then we will characterize the developed silica water filter. Alright, these are the raw materials that we will use for this research study. First of all, these are the amorphous silica gathered from Pasir-Tumbuh, Kelantan, and then this is the kaolin clay that will be used for act as filler for this research study. Alright, these are the flowchart for the silica preparation. First of all, from the rice husk waste product, we will dry the rice husk waste at 120 degrees Celsius for 24 hours. And then we will burn the rice husk waste product at 500 degrees Celsius temperature. And then crushing the process for the fabricated amorphous silica. And then sieving until 63 micrometer. And then if from the XRD analysis, if the rice husk waste product has continued for amorphous, we will use the amorphous silica for fabricated the silica water filter. Alright, As stated earlier, these are the compositions that will be used for this research study. And then for the sintering temperature, we will use 900, 1000 and 1100 degrees Celsius. And then the heating and cooling rate for this research study, which is 5 degrees Celsius per minute. And then these are the proposed design for this silica water filter, which is 100 centimeter in height and then 50 centimeters in diameter. Alright, so these are the mold fabrication for this research study. First of all, we will use the master mold and then we will fabricate the working mold for producing the silica water filter. Alright, these are the examples for the fabricated silica water filters, which is consisting of 50 weight percent of silica, 60 weight percent of silica, and 70 weight percent of silica. For this research study, the two stages sintering profile will be used to produce the fabricated silica water filter. And then for the morphological analysis, we will use the SEM Hitachi SU1510 model. And then this is the auto-fine quarter to remove the electron that will be used for the SEM method. These are the Broker D8 Advanced X-ray diffractometer for the phase analysis, which is XRD. And then for Archimedes theory of this research study, we will use the XX64 Mittler-Toledo electronic balance to get this formula, which is this is the formula for bulk density analysis, and then this is the percentage of porosity analysis for this fabricated silica water filters, which is WD is gathered for dry weight, WS is soap weight, WW is wet weight, and this symbol, which is density of water. Next, we will take a look at the result and discussion for this research study. Alright, firstly, we will take a look at the list of testing and analysis for this research study. First of all, for preliminary testing, we will undergo the performance of mold for this research study, and then for phase analysis, which is X-ray diffraction XRD, for morphological analysis, which is SEM and EDX, and then for physical testing, we will use the bulk density and apparent porosity analysis. For preliminary testing, which is the performance of mold, we will use the synthetic silica in the working mold, as shown in this figure. And then these are the fabricated green body of the silica water filter. For phase analysis of amorphous silica, we can see that this is the amorphism halo for the amorphous silica that have been produced by 500 degrees Celsius of temperature. And then these are the tables for characteristic of amorphous silica as derived from rice husk waste product by XRD analysis. For density analysis, we can see that all samples have reached the optimal range value for the fabricated silica water filter, which is from 0.8 gram per cm cube and then until 1.3 gram per cm cube. For porosity analysis, we can see that 50 weight percent of silica from 900 degrees Celsius of temperature have exceeded the optimal value for this fabricated silica water filter, which is the optimal value of the porosity analysis, which is ranging from 50 until 65% of porosity value. Alright, so for morphological analysis, which is SEM, scanning electron microscopy, we can see that all samples contain silica, and then we can see that with the lower weight percent of silica, will be producing more pore size and then more pore samples. Alright, this is the SEM for 1000 degrees Celsius samples, and then these are the figure that will be produced for the fabricated silica water filter by the sintering temperature of 1100 degrees Celsius. Continue for morphological analysis, we will use the EDX analysis, which is energy dispersive X-ray. From this table, we can see that all samples have gathered the element of silica and oxygen, which is we also know the silica is silicon dioxide. So for the conclusion of this research study, amorphous silica was successfully produced by the burning rice husk at the temperature of 500 degrees Celsius. Secondly, the slip casting method have been successfully fabricated the silica water filter, which includes the mixing, pouring, and sintering process. Next, the analysis results have been gathered that the ADX analysis confirmed the presence of silica and oxygen in all samples. For the bulk density, all samples have been produced and been gathered for the range from 1.22 gram per centimeter cubic to 1.3 gram per centimeter cubic. For apparent porosity, all samples have been gathered for the range of 66.54% to 51.02%. That's all from me. Thank you, everybody. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you very much for your presentation. Okay, the good presentation is more on the technical. I just one question for you. There's how you prepare the sample for the SEM. It look like what is the surface or cross section, because it look like it's not a homogeneous surface.
Alright, thank you, Prof. Hassan, for the question. So for the SEM's analysis samples, I will break the fabricated silica water filter for the cross section to analyze the SEM of all samples.
You just break the sample and then that is your preparation. There is cross section or a fracture surface. You need to know that there is difference.
Oh, so for the SEM samples, I will use the cross section to break the samples and then you scan the samples.
You break, but you not prepare the surface, isn't it? You prepare the surface like the polish, make sure that you cut, or you just break the sample. If you break the sample, they call that surface, fracture surface. You need to be careful because there is because you want to use to analyze it. You make sure that you prepare very thoroughly and then make sure that the same condition of the preparation. Break the sample is not the good preparation, because they go for where they want to go to during the breaking process. Okay? Okay, thank you.
All right, thank you, Professor.
Okay, Assalamualaikum, Muhammad Syahmi.
Waalaikumsalam.
Okay, my question is just a simple one. If you have 1 kilogram of rice husk, how much silica can we get from it?
All right, thank you, Dr. Azam, for the question. So, if we gathered 1 kilogram of rice husk waste product, we will get around 10% of silica, which means in 100 grams of amorphous silica.
Okay, since you only have 10% output, so this is a very economical way of doing things.
Sorry, Dr. Azam?
Since the output is just 10%, so is it economical to use this method to produce your product?
Alright, thank you, Dr. Azam. This research study is very economical because, as we all know, the rice husk waste product, the traditional farmer literally just burn in open air of the rice husk waste product. So that's why if we control the burning of the rice husk waste product, we can use the amorphous silica that has been produced to fabricate the silica water filter.
Okay, thank you, Syahmi, for your presentation. So from my part, I would like to ask regarding the reliability of your products. So, how far is your product can compete to the current use filter in the market? Thank you.
Alright, thank you, Dr. Azham, for the question. So, this fabricated silica water filter will be used at the outside of the household, which means this silica water filter doesn't directly compete to like kuku and kowe. So that's why we will use only only to relegate the contaminants from direct water.
All right. Thank you, Shami. My question is, how the filtration efficiency was tested? Have you tested the efficiency of the filtration? Thank you.
All right, thank you, Dr. Azra, for the question. So for the flow rate of this silica water filter, we have been produced the system to see whether this water filter have been successfully filter the water or not, and we have successfully filtered the water.
All right, thank you.
Thank you, Dr. Azra.
Okay, thank you very much for your presentation today.
Thank you for your time.
Well-prepared presentation. With that, we have reached the conclusion of all presentation for the UTHM Material Lecture Competition 2025. We will now take a short break to allow our judges to deliberate and finalize the scores. Please stay with us as the result will be announced shortly. Thank you. Assalamualaikum warahmatullahi taala wabarakatuh, and a very good afternoon to everyone. Distinguished guests, respected judges, esteemed participants, and dear audience members. We kindly invite all guests to prepare as the closing ceremony of the UTHM Material Lecture Competition MLC 2025 will begin shortly. Please ensure that your devices are set to mute to avoid any disruption. Thank you for your cooperation. On behalf of the organizing committee, I extend our warmest welcome to all of you to this closing session. Before we proceed to the announcement of the winner, I would like to take a moment to sincerely acknowledge and thank our esteemed panel of judges for their dedication, wisdom, and impartial evaluation throughout the competition. We are truly grateful for your time, effort, and commitment in ensuring the success and fairness in MLC 2025. At this moment, I would like to invite Associate Professor Dr. Izzuddin Bezaman, Deputy Dean of Development, Research and Publication, accompanied by Associate Professor IR Dr. Sufiza Ahmad, Advisor of UTHM IIM Student Chapter, to present gift of appreciation to our judges. Okay, our first panel will give to Professor Dr. Hassan Zuhudi Abdullah. Okay, next, our second panel goes to Dr. Nur Azam Badaruzaman. Next, our next panel is Dr. Muhammad Azham Azmi. And last, the one and only, our panel, Dr. Azura Ismail. Thank you for all the judges. Ladies and gentlemen, the results are in, and now comes the moment we have all been waiting for. We will begin with the consolation prizes. We invited Mr. Lo Kai Zuan Denny, thank you. Next, we invited Mr. Muhammad Syahmi Sufi Abdul Syukur. Okay, our next consolation prizes goes to Mr. Chua Ying Hearn. Okay, this is the second runner-up for UTHM Material Lecture Competition 2025. Goes to Mr. Ahmad Fatan bin Ahmad Fazuli. Congratulations. Next, second place. Please give a big round of applause to our first runner-up. Goes to Miss Saraswati, anak perempuan berwarna hitam. And finally, the moment of truth, the champion of UTHM Material Lecture Competition 2025 goes to the outstanding Natasha Salsabila. Congratulations once again to all our winners and participants. Your passion, hard work and creativity have truly made MLC 2025 an inspiring event. Before we officially close, I would like to invite Associate Professor Dr. I.R. Sofiza Ahmad, Advisor of UTHM IMM Student Chapter, accompanied by Professor Dr. Hamimah Abdul Rahman, Co-Advisor of UTHM IMM Student Chapter, to deliver gift of appreciation to Associate Professor Dr. Izzuddin bin Zaman, Deputy Dean of Development Research and Publication. Thank you. Okay, on behalf of the organizing committee, thank you to everyone who has contributed to making this event such a success. Our judge, participants, audience and supporting teams. Also, I sincerely apologize for any shortcomings or unintended mistake that may have occurred throughout the competition. With this, I officially include my duty as the Master of Ceremony for the UTHM Material Lecture Competition 2025. Until we meet again the next edition, thank you for your attention, participation and support. Assalamualaikum warahmatullahi taala wabarakatuh, and have a wonderful day ahead. We will now proceed with our virtual photography session. Thank you.